Now it is your turn to build and stress these operations, and see we have 3 labs. Take your time with each one before you look at the solution. In the first lab, you build the 3 core operations yourself, starting from an empty heap rather than a pre-built array. This checks that each operation keeps the heap invariant on its own. Your first function is heapinsert. It takes the array, the current size n and a key, and it returns the new size. The second is heapextractmax. It returns the largest value, and it assumes the heap is not empty, so n is greater than 0. The third is heapextractmax. It removes and returns the largest value, and again it assumes the heap holds at least one element. To test, insert the values 5, 3, 8, 1, 9, and 2, one at a time, and print the array after each insert. Then peek once and extract the max twice. Before you run it, try to predict the peak result after all 6 inserts. It has to be the largest value you inserted, which is 9. Give the whole thing a try before moving to the solution. This is one clean way to write it. Compare it with your own version as we go through the key lines. This is heapinsert. It takes the array, the size m, and the key. First, it writes the key into A at index n. That puts the new value in the first empty slot, at the end of the heap. This line is worth reading carefully. I gets in, and then n increases by 1. So I holds the old size, which is exactly the index of the new leaf. Inside the loop, parent is I minus 1 all over 2. That is the 0-indexed parent formula, the correct one. If A at parent is greater than or equal to that I, heap order already holds, so we break out of the loop. Otherwise we swap the child with its parent and keep going. That is the new leaf bubbling up toward the root. Now extract max. First it saves the root, A at index 0, into max, because the root is the largest value. Then it moves the last leaf up into the root slot. That keeps the array dense, so completeness is repaired straight away. It shrinks the size by 1. And it calls max-heapify at the root, to sift that moved-in value back down until heap order is restored. Then it returns the value we saved at the start. Look at the output after all 6 inserts. The array is 9, 8, 5, 1, 3, 2, with the largest value 9 sitting at the front. Peakmax reads that front slot and reports 9, exactly as we predicted. The first extract max returns 9, and the heap reorders itself around 8. The second returns 8, and notice, reading up the list, that most inserts bubbled up only 1 or 2 steps. They are cheap. In the second lab, you sort an array in descending order. You build a max heap once, then call extract max over and over until the heap is empty, tracing the heap after every single extraction. Your function is heap-sort by extraction. It takes the array A, its size m, and an output array called out. Given an array of 10 integers, build a max heap, then repeatedly extract into the output array, printing the shrinking heap at each step so you can watch it work. Before you run it, predict 2 things. What is the first value extracted, and what is the last? The first is the global maximum, and the last is the global minimum, because each extraction removes the largest value of what still remains. Try tracing the first couple of steps by hand. Let's look at the solution. It is surprisingly short, because it just reuses the operations you already built. This is heap-sort by extraction, taking the array, its size, and the output array. First it calls build max heap once, turning the raw array into a valid max heap. It keeps a separate counter live for how many elements are still in the heap, because the heap shrinks as we extract. Then the loop calls heapextractmax each time and stores the result into out at index k. Since extract always removes the current maximum, the output comes out in descending order. Look at the trace. After build heap, the largest value, 16, sits at the front. The first extraction pulls out 16, and the remaining heap reorders itself with 14 now at the top. After all 10 extractions, the output is fully sorted, from 16 down to 1. Each extraction is big, O of log n on a shrinking heap, and there are n of them, so the whole sort is big O of n log n. That is the heap sort algorithm. The third lab is a challenge. You extend the max heap to hold records instead of bare integers. This is a realistic priority queue, where heap-order compares just one field of each record. Define a task with a name and an integer priority. Then build a max heap of tasks that is ordered by the priority field. Your first function is pqinsert. It takes the array, the size, a name, and a priority, and returns the new size. The second is heapextractmax. It removes and returns the task with the highest priority. To test, insert 5 tasks with priorities 2, 9, 4, 10, and 5. Think of emergency room triage, where a higher number means more severe. Extract all of them, and the order must be strictly decreasing by priority. One hint before you start. Every comparison reads only the priority field, never the whole struct. But when you swap, you still move the entire task, including its name. Give it a try before you check the solution. Let us look at the solution. You will see the heap mechanics are exactly the same as before. This is pqinsert. It takes the array, the size, a name, and a priority. It builds a task called T. It copies the name in with a bounded copy, at most 15 characters. Then it writes the null terminator itself, at index 15. A bounded copy does not always add one, so this line is what makes the string safe. It stores the priority. Then it writes that whole task into A at index n, the first empty slot. And as before, I gets n and then n increases, so I is the index of the new leaf. The bubble-up loop runs while I is greater than 0, just like the integer heap. Parent is I minus 1 all over 2, exactly the same formula. And this is the one real change in the whole lab. The comparison reads A at parent dot priority against A at I dot priority. It looks only at the priority field, not at the whole record. When we do swap, we call swap task, which moves the entire task, name included. Compare only one field, but move the whole record. And we return the new size as before. Look at the service order. Cardiac arrest at priority 10 comes out first because it is the most severe. Then chest pain at 9. Then laceration at 5 and fever at 4. And sprained ankle at priority 2 comes out last. The tasks are served strictly by decreasing priority. That closes the loop back to the emergency room example we opened the chapter with. Nice work getting through heaps and priority queues.